So I would like to welcome our speaker, Ishavani. Ishavani is programmer analyst at Cognizant Technology, and she would be delivering an interactive talk session on digital twins, real bugs, testing simulated IoT environments for real world impact. So to know more about Ishavani, you can go through the below link. Over to Ishavani, you can take it on. Thank you.
Okay, thank you.
Yeah,
Let me share my screen first.
sure, please.
Hope everyone can see the screen, right?
Yes.
Okay. So, hello everyone. A very warm good evening to all. I'm Isaivani Paramasivam, working as a usability and accessibility tester at Cognizant Technology Solutions. In this session, I will share the main ideas, the challenges we face, and the new approaches from my topic digital twins, real bugs, testing simulated IoT environments for real world impact. Together, we will see how simulation connects with practical testing to bring useful results in the real world. So before we jump into the main topic, let's first understand what IoT really means. IoT stands for the Internet of Things. It's about connecting everyday devices like fridges, lights, or watches to the internet. So they can do three things: collect data, share updates, and act smartly on their own. This reduces the need for constant human control. For example, think about a smart fridge. It can track items like milk, eggs, and juice. When something is running low, it sends you an alert, right? So some fridges can even record groceries automatically. And you can see all these updates right on the fridge screen, your mobile app or a cloud dashboard. An easy way to imagine this with an analogy, it's like having a smart shopkeeper inside your fridge. The shopkeeper, it's like the shopkeeper watches the shelves, updates your shopping list, and helps you restock without having to check manually. So,
Sorry to interrupt, Ishwani. We don't see you well. Maybe you're away from camera. Maybe if you can
now
adjust. Um,
this one is,
yeah,
is it okay?
yeah. I mean, you'll have to adjust because your face is getting truncated. Yeah.
Okay, fine.
This is better. Yeah.
Now, fine.
Thank you.
Okay, okay, thank you. So, okay. Now the third slide is, we all know how IoT devices like a smart fridge work, but here is the challenge. IoT devices are always connected. They don't work alone, right? So even a small bug in one device can spread and cause big problems across the whole system. This is called, we can tell it as butterfly effect, which means one tiny error can ripple into many failures. So traditional testing usually checks devices one by one, right? For example, it might say the fridge sensor works fine, but it doesn't test how the fridge, the mobile app, and the shopping system and the delivery service all work together. In reality, IoT devices are part of networks. They never operate alone. So that's why we need a smarter way to test digital twins or virtual copies of devices. They let us safely simulate thousands of IoT systems, add faults, and predict failures before they happen. In simple words, they help us catch the butterfly before it flaps the wings. So we have seen the butterfly effect. How one small bug into IoT can ripple across devices and cause big failures. Traditional testing often misses these issues, but because it only checks devices in isolation. But IoT systems live in networks, not alone. So, how do we test them smarter? This is why my framework contains comes in TPTF, that is the Twin Driven Predictive Testing Framework. It's a smart way to test IoT systems. Here is how it works. We create digital twins, which means virtual replicas of devices, so we can test safely without touching physical hardware. AI then predict usual behavior before it comes a failure, giving us early warnings. We rely on open source tools like Eclipse Ditto, MQTT, which is we can say it as Mosquito Broker, and PyTest, Node-RED, scikit-learn and Grafana, which is flexible and accessible for any team. With Docker-based simulations, we can scale up to thousands of devices without needing real hardware. This makes testing safe and cost-effective. This is ideal for freelance testing also. And finally, it is interactive and visual dashboards show systems health in real time, and we can inject faults to see how system reacts. We have introduced TPTF. Let's see how it works step by step. We start the Eclipse Ditto, which builds digital twins, virtual replicas of devices that mirrors their states. Then we use MQTT, I already said, right, Mosquito, to simulate communication between devices at scale, just like in real IoT network. Think of it like a post office for devices. Instead of talking directly, each device sends its messages to the MQTT broker, and the broker delivers them to whoever needs them. For example, if we take a e-commerce site application, the cart services publishes a message, shoes added to cart like. The inventory services subscribes to that topic so that instantly it receives the messages and checks stock. The payment services subscribes to checkout messages. So when the cart says checkout started, payment begins right away. And the next thing is our PyTest automates test cases to check how devices behave and responds to faults. With RoadNet, with Node.net, we can create real-world problems inside our test environment, like network drops, GPS errors, or payment timeouts. These are the kinds of issues that usually go unnoticed in staging, but we can cause big trouble in reality. To stimulate this, we first run our service containers. For example, the cart services in one container and the inventory service in another container. Node-RED itself also runs in a Docker as a container. So next we connect Node-RED to MQTT. We drag an MQTT in block to listen to message like shoes ordered to cart, and then MQTT out block to send messages like payment success or even faulty ones. Both block points to the broker, such as Mosquito. Now we can inject faults with using the red node flows by adding blocks like delay, drop, or change. For example, we delay the inventory replay, so checkout happens without of stock items. This shows how our Docker services react to our problems. Once these faults are injected, we collect the logs, things like response times, error codes, or transaction results. For example, a checkout that completes in 2 seconds is marked as normal, while a checkout that times out after 10 seconds is marked as faulty. The labeled data set is given to scikit-learn, which is the Python toolbox for AI. We need the data set into the model, train it to learn the difference between normal and faulty behavior, and then test it to make sure it predicts correctly. Finally, we integrate the trained model back into our Python application. Now, whenever the system runs in real time, the AI model watches the data and tries us alerts the moment it spots unusual behavior, which helps us prevent failures before they impact customers. And to make this even more powerful, Grafana dashboard which is one of the open source tools, which gives us real-time visualization of system health and test results. This way, testers and stakeholders can see the live status, track anomalies, and confirm that the AI predictions match what is happening in the system. Together, these steps create a complete pipeline from building twins to predicting bugs, making IoT testing smarter, safer, and more reliable. So now to make this concept more relatable, let's take a live example from the e-commerce world. Imagine you are shopping online, searching products, adding them to the cart, applying a coupon, and finally checking out. Behind the scenes, there are hundreds of components working together to make this experience seamless. In our simulation, we didn't just test one button. We recreate the entire store virtually. So the point one is we can simulate 700 plus compounds, the search bar, like the search bar, product catalog, cart payment gateway, and even the recommendation engine. For example, imagine a user searching for shoes, adding them to cart, applying a coupon, and checking out. All of these flows were testing together virtually. But testing is not complete unless we know how the system behaves when things go wrong. So the fault injection comes here. So next, we intentionally introduced failures to see how the system reacts. For example, we dropped items from the cart mid-checkout, delayed payment confirmations, and even broke the inventory sync between the warehouse and the website. This helped us test how resilient the system really was. So these fault injections revealed hidden issues we wouldn't have seen otherwise. For example, when the inventory sync lagged, the cart still allowed checkout for out of stock items. We also discovered bottlenecks like when too many users tried to check out at once, the system slowed down significantly. These are the kinds of bugs that only surface when you test the system as a whole, not just individual components. And the best part is finding these issues early gives us a chance to fix them before launch. So outcome, which is 50% fewer older order failures, right? So by addressing these flaws ahead of time, order failures dropped by half. So customers longer saw frustrating messages like payment failed or item unavailable during checkout. Instead, purchases went through smoothly, creating a seamless smoothing experience. This is the real impact of simulation testing. It doesn't just find bugs, it improves customer trust and satisfaction. Sorry. So after discovering and fixing bugs, the next step was to keep a close watch on the system during simulation. Real world dashboards, right? So we use dashboards to visualize the system health live as the simulation run. For example, Grafana dashboard shows metrics like cart activity, payment response time, and inventory sync status. This meant testers couldn't spot issues instantly instead of waiting for reports after the two test was completed. Dashboards gives us visibility into what was happening right now, but what if we could also predict problems before they grow bigger? So, point six, predictive alerts. That is where AI helped. It flagged the risky patterns before they have become major issues. For example, if many users suddenly started leaving items in the cart without checking out, the AI noticed this unusual rise. It immediately sent an alert to testers saying card abandonment is higher than normal. This gave testers the chance to investigate and fix the issue. Maybe a coupon wasn't applying or payment was low before customers even complained. So So traditional testing sometimes misses the problems that real users face, right? So the twin predictive testing framework changes that. It makes sure that works in testing also works in reality. So it will catch real bugs early. TPTF finds issues that normally testing misses before customers even ever sees them. It works everywhere. It can be used in many fields like healthcare, education, banking, gaming, etc. So it is easy to use. It is a open source and scalable. So any tester or team can adopt it, download it, and use it for that purpose. And it is clear, and team friendly. Dashboards and simulations make testing visual, simple, and easy for teams to work together. And the future is ready. Most importantly, it builds strong systems that can handle real world challenges. That's why TPTF is not just another framework. It is a real game changer for you. So, to summarize, IoT systems are powerful but fragile. Even small bugs can ripple across networks. Traditional testings often misses these issues. So, we need smarter methods. That is where TPTF or TPTF comes in. By combining digital twins, AI predictions, and fault injections, it makes testing scalable, cost effective, and predictive. Our e-commerce simulation showed 50% fewer failures, providing its real world impact. In short, TPTF ensures that What works in testing also works in reality, building resilient systems ready for the future. So that's it, folks. Thanks for listening and engaging. Thank you all for taking the time to listen and engage. So, and your attention means together. We can keep learning, sharing, and building better ideas. So that's it. If anyone can, if you want any questions.
Thank you, Isaivani. I think
Okay.
that was very helpful. Um,
Okay. Thank
we
you.
yes, we don't. Okay, we have a question
Okay.
regarding fault injection. Can you
Okay.
please provide some more examples?
Um, if we want to give a network signal fault, right, there will be more blocks. There will be many faulty blocks are there in red nodes. We can choose any faulty blocks like network failure and the payment, slow payment, right, and the drop, sudden signal drop, like that, and we can drop the fault and inject in our code, and we can test accordingly. As it is a very open source and easy to install, we can test it any failures before it happens, right? Sorry, I'm not able to hear your voice.
We can hear you.
Sorry, I was talking
Uh,
on mute. Yeah. So is there any strategies that will help you validate your accuracy and fidelity of these digital twin simulations?
there is nothing like that strategy, as it is in the we are yet to implement this plan in our project. It is a so there is, I don't think there is no new strategy to implement this.
Okay.
Mm.
But is there any approach with which you kind of do a comparison or
No, there is nothing like that.
okay. Can this also be integrated with CI/CD?
Yeah, we can integrate.
Okay. Is there any metrics that should be tracked again to figure out, real world reliability from your digital twin tests?
There is, I'm not aware of that and all, because we are, I already told, right? So it is a new plan in our project and it is yet to implement, right? So we too are searching for that. If I get any idea, I will let you know for sure. I will
Sure.
drop your mail ID, my mail ID, and we'll let you know in future after
Sure.
we implement this, right?
Sure. Thank you so much, Isaivan. Is
Thank you.
there
Thank
any
you.
other questions that we want to address?
If you can share more insight on the architecture of this entire solution, right?
Uh,
That
uh,
would be great. It would be insightful
okay.
with the tools and everything, because I
Mm,
think the slides covered more on the conceptual bit of it,
mhm,
right?
mhm.
So if you can talk about from an architecture point of view with respect to IoT, correct? So that would be great.
Okay, I will check and let you know in future for sure. So this is what we have covered in our project, and this is a new implementation in our project, right? So I will research and let you know in future.
Sure, Isha.
Okay, thank you. Thank you so much.
Thank you.
Prima, we can probably bring up the slide informally then.
Sure,
Sure,
sure.
sure, Deepti. Yeah. Yeah. Thank you so much, Ishavani, for your wonderful session.